Hi everyone. In this lecture we are going to discuss effect of temperature on reaction rate and Arrhenius equation. Friends, this lecture is common for SY-BSc and TY-BSc chemistry students. So here let us consider number 1, effect of temperature on reaction rate. So here all of you know that when we have discussed the factors affecting on the rate of chemical reaction, already we have discussed the first factor, that is the temperature, which affect on the rate of reaction, and all of you know that as we increase the temperature, generally here the rate of the reaction is also increases. So here in some homogeneous reaction, the rate become double or triple for each 10 degree Celsius rise in temperature. That means here for a chemical reaction, if we increase the temperature by 10 degree Celsius, the rate of the reaction, it may be double or it may be triple. So here this increase in the reaction velocity or the reaction rate with temperature, it is expressed in terms of the temperature coefficient. So here let us define the term temperature coefficient. What is meant by temperature coefficient? So here temperature coefficient, it is the ratio of a rate constant of reaction at two different temperature separated by the 10 degree Celsius. Generally here the two temperatures are considered 25 degree Celsius and 35 degree Celsius. So the temperature coefficient, generally it is the ratio of the velocity constant for the same reaction at two different temperature. So here velocity constant at 35 degree Celsius to the velocity constant at 25 degree Celsius, and this ratio is equal to 2 or 3. So here this term, it is called as the temperature coefficient. So here the value of the temperature coefficient in most of the reaction, it may be equal to 2 or it may be equal to 3. In some reaction it is more than 3. So let us consider some examples. So the first example here, dissociation of hydrogen iodide. So here in the dissociation of hydrogen iodide, the temperature coefficient is 1.8. That means here if we increase the temperature of this reaction by 10 degree Celsius, so here this ratio is equal to 1.8. Then the second example, reaction of methyl iodide with the sodium ethoxide, this ratio, that is the temperature coefficient, it is a 2.9 for this reaction. I would like to tell you the one more example, the temperature coefficient for the decomposition of nitrogen pentoxide. So here in the decomposition of nitrogen pentoxide, the temperature coefficient, it is a 3.8. So these are the three examples. Friends, here when we consider the temperature coefficient term, so temperature coefficient, it has certain limitations. The first limitation is that temperature coefficient is an approximate method for expressing the effect of temperature on the reaction rate. It is not perfect method, it is an approximate method just to explain the effect of temperature on the reaction rate. This is the first limitation. Second one is temperature coefficient fails to explain that the number of collisions in reaction is increasing by 2%, whereas the reaction velocity is increasing by 100% or 200% or more than 200%. So these are the two limitations of the temperature coefficient. These two limitations of the temperature coefficient points to led Arrhenius to suggest his own equation to express the effect of temperature on the reaction velocity. So here the Arrhenius developed an equation. That equation is called as the Arrhenius equation. The equation gives the variation of rate constant with the temperature. The equation is similar to one-top isochore that gives variation of equilibrium constant of reaction with the temperature. So here let us consider the Arrhenius equation. So this is the diagram. So energy versus progress of the reaction or the reaction coordinate. Here the reactant, here the transition state or excited state or activated state, and the product. So here this is the activation energy. So here the energy versus progress of the reaction or the reaction coordinate. So as per Arrhenius, for a chemical reaction, molecular contact and hence molecular collision are necessary. Naturally, the rate of the reaction should be equal to the rate of collision, but in actual practice, in a chemical reaction, all the colliding molecule do not react, only few can react. So, this is as per Arrhenius. So, accordingly, reactant do not pass directly into the products. Reactants must first acquire sufficient energy and become activated. So, here these are the reactant. First they acquire certain amount of energy, they move from the normal level or from ground level to the excited or the transition state or activated state, and then the reactants will be react, and this energy it is called as the activation energy, and then the reactant activated reactants they are converted into the product. So, here let us define the term energy of activation. So, here the minimum energy required to raise the reactant from their normal level to the excited level is called as the energy of activation. So, here in this diagram, this is the energy of activation. This is the normal level or the ground level, and here this is the excited state or the transition state or the activated state. So, here we can also define the energy of activation. Minimum amount of energy the reactant molecule must acquire before they could react, that minimum amount of energy it is also called as the energy of activation. It is denoted by symbol EA. Then the unit for the energy of activations are, generally it is expressed in terms of calorie per mole or kilocalorie per mole. So, here energy of activation it is a characteristics of the reaction, and energy of activation is a different for the different chemical reaction. That is why here we can say that the rate of all chemical reactions are not same. So, different chemical reaction have a different rate because of energy of activation. Energy of activation of all reactions are not same. So, here the reaction with the low energy of activation are the faster reaction, and the reaction with the higher energy of activation are the slower reaction. In short, we can say that when we consider any chemical reaction, if its energy of activation value is small, such reaction is the fast reaction. If its energy of activation is high, then such a reaction is the slow reaction. So, once again let us consider the definition of the energy of activation. It is the minimum amount of energy the reactant molecule must acquire before they could react. That minimum amount of energy it is called as the energy of activation, and it is denoted by symbol EA. So, here next point is derivation of Arrhenius equation. So, let us derive the Arrhenius equation, and the derivation is based on the one top isochore. Consider the reversible reaction A plus B which gives the C plus D. So, here rate of forward reaction is equal to K1 into concentration of A into concentration of B. Rate of the backward reaction is equal to K2 into concentration of C into concentration of D. All of you know that when there is an equilibrium in the chemical reaction, here the rate of the forward reaction is equal to the rate of the backward reaction. So, at equilibrium, this is the rate of forward reaction is equal to the rate of the backward reaction. This equation can be rearranged. K1 by K2 is equal to concentration of product divided by concentration of reactant, or K is equal to concentration of product divided by the concentrations of reactant, when K is equal to K1 by K2. So, here K it is called as the equilibrium constant for the chemical reaction. K1 is the rate constant for the forward reaction, and K2 is the rate constant for the backward reaction. So, this is the equation number 1. For thermodynamic, the one top equation relates the equilibrium constant with change in internal energy, that is the delta E, and here the d ln k by dt is equal to delta E upon RT square. This is the equation number 2. Substituting the value of the k from the equation number 1. So, here k is equal to K1 by K2 in the equation number 2. So, equation 2 can be written as d ln K1 by K2 divided by dt is equal to delta E upon RT square. This is the equation number 3, or equation 3 can be written as d ln K1 by dt is minus d ln K2 by dt is equal to delta E upon RT square. So, here the one top propose that equation 3 can be split up into the two equation, and the two equations are d ln k1 by dt is equal to E1 upon RT square plus I. This is the equation number 4. Here d ln k2 by dt is equal to, here there is a E1, actually it is a E2. So, E2 upon RT square plus I. This is the equation number 5, where delta E is equal to E2 minus E1, where I is the constant, and it was observed that I was independent of temperature. Therefore, I must be equal to 0 in the equation 4 and equation 5. So, equation 4 and equation 5 can be written as d ln k1 divided by dt is equal to E1 upon RT square. This is the equation number 6. And here d ln k2 by dt is equal to E2 upon RT square. This is the equation number 7. So, here equation 6 and 7, E2 and E1, k2 and k1, they are replaced by the EA and K, and the final equation is d ln k by dt. Here k1 is replaced by the K, that is why d ln k by dt, and E1 is replaced by the EA. So, here EA by RT square. Similar way, equation 7 is also written as d ln k by dt is equal to EA upon RT square. This is the equation number 8, and the equation 8, it is a Arrhenius equation, and in this equation the important term is the EA, where EA is called as the Arrhenius, not Arrhenius equation, it is the energy of activation. EA is the energy of activation. This is the Arrhenius equation. Then the exponential form of the Arrhenius equation. Consider the Arrhenius equation. So, d ln k by dt is equal to EA upon RT square. So, here this is the Arrhenius equation. By considering the Arrhenius equation, we are going to derive the exponential form for the Arrhenius equation. So, we have to rearrange this equation. So, the rearrangement, d ln k is equal to EA upon R into dt upon t square. This is the equation number 9, and here we have to integrate the equation 9. So, integration of equation 9, integration of d ln k is equal to EA upon R. EA is constant, R is constant, that is why here EA upon R, it is written out of the integral sign. So, EA upon R, integration of dt upon t square. So, integration of d ln k, it is the ln k, is equal to EA upon R, EA upon R. So, integration of dt upon t square, it is a minus 1 upon t. So, here in bracket minus 1 upon t plus c, where c is the constant of integration. Then this can be written as ln k is equal to minus EA upon RT plus c. This is the equation number 10. So, here for convenience, it is supposed that this constant of integration c, it can be considered as c is equal to ln a, where a is constant and this constant is called as the Arrhenius constant. Hence, ln a is also constant. So, equation 10 can be written as ln k is equal to minus EA by RT plus ln a. This is the equation number 11. This equation can be written as ln k minus ln a is equal to minus EA by RT. So, here ln k by a is equal to minus EA by RT, and the exponential form can be written as k upon a is equal to e raised to minus EA by RT, or k is equal to a into e raised to minus EA by RT. This is the equation number 12, and equation 12 is the exponential form of the Arrhenius equation. So, here in this equation, as temperature is involved in the exponent, there will be rapid increase in the k by small increase in the t. So, here k is the velocity constant, a is the Arrhenius constant, E is the energy of activation, R is the molar gas constant, and T is the temperature. Thus, the tremendous increase in the rate constant and rate of reaction by small increase in the temperature is explained with the help of this Arrhenius equation, that is the exponential form of the Arrhenius equation. So, friends, today we have discussed the effect of temperature on the rate of reaction. Then here the Arrhenius equation, derivation of the Arrhenius equation, and the exponential form of the Arrhenius equation. Thank you.